So I'd like to welcome everyone to this very special lecture in memory of our warm and inspiring friend, Joe Wolfe. I feel his presence so much in this webinar. He was always among the very first people to arrive before each talk, always so deeply engaged, asking questions, and always with his warm smile. Certainly, his influence will continue to be deeply felt in the seminar through the work of so many of us here. Following the talk today, we'll stay on Zoom for a time of sharing thoughts and memories of Joe. I'm also very pleased that Lois is able to join us today. Thank you for coming. I'm very pleased to introduce our speaker, Mike Eastwood of the University of Adelaide, a longtime collaborator of Joe Wolfe, speaking on the range of the double fibration transform.
Okay, right. So thank you, Carolyn. Right, so let's see. Just make sure everything's working here. Yes, I think so. Moving things into an appropriate location. Right, can you hear me okay?
Yes.
Yes.
Good. Okay.
Yes, but
yes.
We cannot watch you. I don't know whether you're doing in purpose.
Oh, I'm doing what, sorry?
You might turn on your
We
camera.
cannot watch.
Oh, my camera. Wait.
Yes, there's simply a little black box that says Mike E.
Yeah. Yes, there is. Ah, I see. Right. Okay, there is indeed. Yeah, that's what's happened. Okay. Just a minute. Here we go. Right, start video. Yeah. Oh, there I am. Okay, so now everything's now working. Is that correct? Yes, you can see me. Yes.
Yes. All is good
okay.
now.
Okay. Good. Right. I'll just put that back where it was. Okay. Okay. Right. So, yeah, I mean, this is a shock to everyone, and to me. I mean, I still can't believe this has happened. So, I was actually at a conference with Joe where I went into August, so just the beginning of August, and that was in country Victoria, in a place called Creswick. The conference ended on a Friday, and the last I saw, Joe was getting into a car with Nikolai Nuryovsky. Getting into a car. I'm really still very upset by this. Getting into a car with Yuri Nikolaevsky, and he was going off to Melbourne Airport. I was actually in the room next to Joe at the meeting, and every morning I would hear his alarm go off at 6:30. So I was up slightly before his alarm went off, and then for 2 weeks we had breakfast together, dinner together, lunch together, and so on. And he, as he often did, he came bearing gifts. His gift on this occasion, or one or two gifts, was this book, which I highly recommend, called What If? And it's about what happens if you do ask absurd hypothetical questions, and this book gives you serious scientific answers to it. It's by Randall Munro. Now, as I just mentioned before, just last week I was in hospital myself with a kidney stone, and so I've not had much time to prepare this talk, but nevertheless, here we go. Now, the title of the talk, The Range of the Double Fibration Transform, has been something which has actually been the title of an article which Joe and I have been working on for, well, a long time, probably about 20 years. And I've just had a look at the latest draft, and unfortunately, the latest draft is dated from just over 12 years ago. Now, we've done some things since then, but we've not actually added anything to the main draft. And so soon I will write a little report type article, which I'll probably put in the matrix proceedings. Matrix is the conference which we were at with Joe. Anyway, I'd just like to tell you about what this article is about, and you know, roughly speaking, where we are up to. Okay, so here's what it is about. Okay, so first of all, it's about flag manifolds. So these are complex flag manifolds. Probably everybody in the audience knows what these things are, but the basic one, like the simplest, is complex projective space. And this is the space of lines, one-dimensional submanifolds inside a complex vector space of one dimension higher, so which may as well take to be Cn+1. Or you could look at the Grassmanion of K-planes. That's just when you increase the dimension a little bit. That's again a flag manifold. Or perhaps a little bit more exciting is the space of lines inside planes inside C3. So that would be F. F stands for flag. 1, 2, C3, lines inside planes. So this is the space of lines L, dimension 1, inside planes P, dimension 2, sitting inside C3. And you can picture these things. And so here's a picture inside C3. There's a line, there's a plane. And the reason they're called flag manifolds is because you can decorate them to make them look like flags. So there is a simplest possible flag manifold. Okay, these things are homogeneous spaces. They're complex manifolds, homogeneous under the action of a transitive action of a complex semi-simple Lie group, let's say. In this case, it's just SL3. The thing that makes them special is the subgroup. The character of the subgroup which you're dividing by. So this is CP2 is that particular quotient, and the flag manifold is that particular quotient. And yeah, so and now I should just leap ahead a little bit and tell you a little bit about, you know, why it is that these things arise in, well, representation theory, and in particular the work that Joe and I were doing. And it all comes down to, well, the Bott-Barel theorem. So let me just tell you a little bit about the Bott-Barel theorem. So, okay, right, so. Okay, so the point is that not only do you have the complex group, SL3C, acting on CP2, or the flag manifold, but well, what turns out to be the maximal compact subgroup of that, SU3, also acts, and it acts transitively. And this is a common feature. So anytime you've got a complex semi-simple Lie group and you look at the compact form of that, it acts transitively on all of the flag manifolds, including CP2 or F123, F12C3 in this particular case. The representations of SU3 can be labeled by the highest weight. So I'm not going to go into that. You either know about this or you don't, in which case I'm not going to explain it anyway. And so what you can do, and this is actually something which was very much a feature of Joe's last talk at the Matrix conference. He gave the very last talk on the Friday, and he talked about the semi-simple complex Lie groups, or simple complex Lie groups. And he noted, as everybody does, that in fact, you know, lots and lots of information can be recorded on the so-called Dinking diagram. And what he did was, in this talk, which is really, really lovely talk, the last talk of the conference, he drew the various Dinking diagrams for the various series of Lie groups, and he explained how you could read things off just by staring at the Dinking diagram. Anyway, the very simplest thing you can do is decorate the nodes with some integers here, non-negative integers, and that classifies the representations of the corresponding group, either the complex group or the compact real form. Anyway, the Barel-Weil theorem, one of its simplest instances is this. So you look at the space of full flags, so that would be this flag manifold F12 inside C3. You let SL3 act on it in the approved manner, and hence SU3 acting on it in the approved manner, and you realize this representation as the space of sections of a holomorphic line bundle over that space. Okay, so I mean, as I was mentioning, everything can be recorded with the Dinking diagrams, and here you've got the corresponding line bundle, which is somehow the space F12C3 is also recorded by in the Dinking diagram by crossing out a couple of nodes like this, which means look at the strictly upper triangular matrices when you quotient. And then it turns out that, of course, well, this is a finite dimensional representation because it's a finite dimensional vector space, because all of the holomorphic line bundles or holomorphic vector bundles on any compact complex manifold have only a finite dimensional space of sections. And it turns out that it's exactly this irreducible representation. If you like, you could use CP2 instead, and that's incorporated also into this Dinking diagram way of looking at things. So CP2, and this time you have a little bit of a vector bundle rather than a line bundle. So Barel-Weil theorem originally started with line bundles. Okay, and then of course, as I was just mentioning, you can absorb a lot of this just into the pictures, the Dinking diagrams. And so you can just write sections of, and incorporated in this is holomorphic sections, and so on and so forth. Or you can just write that as an abbreviation for these two statements about the Barel-Weil theorem for SU3. Okay, so that's the Barel-Weil theorem. Now, what about the Bott-Barel-Weil theorem? Well, Bott modified the Barel-Weil theorem to say that, well, instead of just looking at sections, you can look at more complicated, seemingly more complicated gadgets, only slightly more complicated. But what you can do, instead of looking at sections, you can look at, well, in this case, since the space is three-dimensional, you can look at first cohomology, second cohomology, or third cohomology. These will all be finite dimensional vector spaces. And so you get 6 different realizations of this finite dimensional vector space. All of these things are of this representation. All of these things are different realizations of the same gadget. And you can choose which is your favorite. So someone has drawn, oh, I don't know, someone's drawn on my screen somehow. What's happened? Wait. Okay. I did that, didn't I? Oh, okay. Anyway, all of these things are the same things. These blue lines are actually equality signs. Okay, and you can choose whichever is your favorite, really. You'll notice that these things fit together in a sort of familiar looking pattern. You'll recognize the Weil group of the of SL3 sitting here. It has 6 elements. These are how the 6 elements are joined together in the Bruhat ordering and so on. And the relationship between the left-hand end, where you're looking at sections, and the right-hand end is given by basically by Serre duality. Anyway, the final conclusion from this, and then we'll get back to a little bit more elementary considerations. The final conclusion is actually that probably the best way to realize this irreducible finite dimensional representation of this either complex Lie group or its real compact real form is by means of the top dimensional cohomology for an appropriate line bundle. Okay, so that thing at the right hand end of the screen there is, I maintain, actually the best realization. And the point is that it works for non-compact Lie groups as well. Whereas if you're sticking with the barel theorem, then it doesn't work. I mean, the Bott-Barel theorem is the best thing. It's the best to use this dual approach. Okay, we'll get to that soon. Okay, but anyway, let's now backtrack a little bit. And as I was saying, you know, the best way of thinking of all of these flag manifolds is by means of their Dinking diagrams. So let me just have a little bit of a rave about that. So here are some flag manifolds where, well, the first sort of thing you might do is mod out SLM plus 1C rather than SL3C. You may mod it out by a block upper triangular matrix like that. And that will give you some nested, it's a space of nested sequences inside CM plus 1 of various fixed dimensional gadgets. Okay, and then you can record that in the Dinking diagram. So obviously you can record this upper triangular matrices by putting down these little crosses like that, and then put little circles wherever you haven't got a cross, and you just transcribe that onto an appropriate Dinking diagram. And so here is a Dinking diagram with n nodes that represents SLM plus 1C. And crossing through some of these nodes precisely describes which subgroup you're looking at and consequently which flag manifold you're looking at. So everything is recorded onto a Dinking diagram. There it is. And the point is, the really good thing about, of course, about Dinking diagrams is that you can just use them to, even if you've not got a matrix group, you know, you've got some exceptional group of some form, you can use them to record what's happening with the flag manifolds and everything else about these things. So, for example, here are the Lagrangian Grassmanions. So that's homogeneous for symplectic action. Quadrics, which are homogeneous for the orthogonal actions. There's the odd dimensional ones. There's the even dimensional ones. Some exceptional examples, like that's for E7. That's an example for E7. All of these things are actually compact Hermitian symmetric spaces, which again was one of the main topics of Joe's last talk at Matrix. And here's one that isn't. You can cross through any of the nodes. All right, so I take it we all have a reasonable understanding of what flag manifolds look like. Now, what about what can you do with these things? Flag domains. Okay, so flag domains, or these are maybe Wolf domains. So you start with the flag manifold. There it is. G mod, let's say Q for a complex parabolic subgroup. I don't know why we started calling it Q rather than P, but that's the way around we've got it in our draft article. So here is a complex semisimple Lie group modulo one of these complex parabolic subgroups. In other words, as typified by the previous examples. Anyway, the new ingredient now, as I was indicating with the Bott-Barel theorem, is to look at an arbitrary real form of G. So not necessarily the compact real form. That's kind of boring, actually, but look at something a bit more exciting, some non-compact real form of G, generally speaking, and just let it act on Z. And here's the main theorem from the 1960s at some stage by Joe Wolf, is that in this complete generality, there are only finitely many orbits. Of course, his article where this is proved goes into a lot of detail about what these orbits look like. They're quite complicated, I have to say, but some of them, at least, since there are only finitely many of them, are open orbits. So these open orbits, they are complex, nice complex manifolds, non-compact complex manifolds on which G0 is acting transitively. This thing is called a flag domain. And let's see, there's There's a book here, which I'm just going to hold up in front of the camera, by Gregor Fels, Alan Huckelby, and Joe Wolfe, called Cycle Spaces of Flag Domains, and it's from 2006. And it goes into a lot of detail about these things. So I'm not going to go into a lot of detail, but if you want the ultimate reference on these things, then you should look at that book published by Berkhäuser in 2006. Anyway, so this flag domain, which I'm going to denote by D, is now a complex submanifold, complex open subset of this compact complex manifold, and G0 is acting transitively. Let me give you some examples. So we'll go back to our very simplest flag manifold, which is CP2. And if you just look at the, rather than the compact form, which was SU2, I'm going to look at SU21. That has 3 orbits, it turns out. So if you fix a Hermitian form, signature 2-1, then you can either look at those lines on which the Hermitian form is 0, which is positive definite, or which is negative definite. And you'll get 3 orbits. So a closed one, which is marked in yellow, which intrinsically is a sphere. So that's I've suppressed a dimension here. It looks like a circle, but actually it's a sphere. And then there's the internal part of that sphere, which is a ball. And there's the external. These two are open, and these are therefore flag domains. Okay. Let me look at something a bit more exciting. I'm just going to up the dimension by 1. And when you up the dimension by 1, you get some sort of intersection with some physics constructions, and in particular twistor space. So let me now up the dimension by 1, look at CP3. As I said, if you look at the compact form of the group, which is SU4, then that acts transitively. So that's boring. So SU4 is actually the you should perhaps think of it from physics point of view as the double cover of SO6, so it spins 6. Anyway, 1 orbit. It's still a flag domain, but it's not interesting. Now, unusually, and this is very unusual, there are other non-compact real forms which also act transitively. So SL2H, which is sitting inside SL4C, by identifying C4 with 2 copies of quaternions. So that is a non-compact real group. You can think of it as spin 5-1 if you want. That also acts transitively, but that is unusual. That's why there's a couple of exclamation marks after it. So something which is a bit more interesting perhaps is SU22, which is the same as spin 4-2. And that has 3 orbits. It's a little bit like what we had on the previous slide for CP2, but this is for CP3. And you get an orbit where the associated Hermitian form is positive definite, where it's negative definite, or where it is null. And so, again, there are many dimensions suppressed here. That yellow thing is actually 5 real dimensional, but there are 2 open orbits. The one other thing which has been omitted from this list is the other obvious real form, so-called split real form, which is SL4R, same as spin 3-3. And there are just 2 orbits, one closed and one open. So real projective space, RP3, is the closed orbit, and the complement is the only open orbit. Generally speaking, there's a whole bunch of open orbits, there's a unique closed orbits, and then there's some things in between. So this is what you get. This is basically what you get for CP3 as a flag manifold and its various different real forms acting on it. Now, right at the beginning, we had Grassmanions. So let me just look at Grassmanions and see how they fit with this. So again, I'm going to look at this sort of most interesting of the real forms of SL4C, namely SU22, and let that act on this flag manifold. And you can picture that by looking at how it looks on CP3, which we had on the previous slide. And what you can either have, so you can think of the two planes inside C4 as the lines inside C3. And those lines can either lie, there's a number of different sort of generic arrangements. One of them is that they lie entirely in the upper half plane, that's as upper half space as pictured, or entirely in the lower open orbit in complex projective space, or they can do this. They stray from one to the other. These are the open orbits. You can see things are getting a little bit more complicated, and there are three of them. The other possibility is you could have a line entirely inside this yellow bit. So that's a CP1 lying inside this five-dimensional CR manifold in the middle. Or you can have things which just touch on one side or the other. Anyway, there are three flag domains, and there are six orbits. These three open ones, there's one closed one where the line lies inside the yellow CR manifold, or you can just touch from one side or the other side. Those are the other two, neither closed nor open orbits. The closed orbit has a geometric interpretation. So again, this is linking everything with physics. The closed orbit is actually a compactification. It's a four-dimensional orbit, and it's a compactification, a natural conformal compactification of Minkowski space, because spin42 or SO42 is the natural conformal group here. SU2 is acting by conformal automorphisms on this compactified Minkowski space. And so you can think of this M, which is this original Grassmanion, as being compactified Minkowski space. And then all of this somehow has something to do with physics, and in particular, conformally invariant physics, because everything is being acted upon by this conformal group. Right, now, so much for flag manifolds. And what about cycle spaces? So the ingredients so far are a flag manifold, so which you can represent as a decorated Dinking diagram like this, and a flag domain, which is a real form, which of course you can also decorate your Dinking diagram accordingly, but I won't do that. So this is for a real form of G. Now here's another theorem due to Joe Wolf, and that is, if you look at the pick a maximal compact subgroup of G naught and look how it acts, that will give you various submanifolds of your flag domain. So, for example, in this this canonical case which I've been carrying along, SU22, you could just look at S of U2 cross U2 sitting inside that block diagonal, and let that thing act, and that will give you some special things inside your flag domain. And one of those special things, one of these special orbits, one of these orbits is special in that it is actually turns out to be complex. So there's exactly one orbit which is complex, and it's generally, standard notation is C sub 0. C stands for cycle. And what you're going to do in this theory is you're going to probe your flag domain D with these cycles, with these compact submanifolds. And this is the base cycle, and then you move them around by the group. Now, strangely, you don't move them around by this compact group. What you do is you try and see what happens if you move them around by the complex group. Okay, so this gets a bit technical now. You move them around by the complex group. You look at those things which remain inside D. Okay, so still probing within D. And then in addition, you have to take the connected component containing the base cycle. That's what that little superscript 0 has to do. This is called the cycle space. This all comes to life when you look at particular examples. Let's look at a particular example. So the example is the one we've been carrying along, which is to take the upper half of complex projective 3 space like that. Then the base cycle is that yellow line lying inside the upper half piece, P plus, and all of these green things are the translates of that by the complex group G, and you're looking at those things which remain inside. Okay, now, so this gives you actually something that we've seen before, namely it gives you a particular Lag domain in the Grassmanion, right? Because all of these cycles, they correspond to just points in the Grassmanion, and you're looking at those things which are entirely in the upper half space. Okay, so that's something we've already given a name to. So it's an open subset inside what I started to call complexified, compactified Minkowski space. Okay, this picture, which I've drawn here, is actually, and this is one of the problems with our article, is that it's misleading. It's not nearly as, the general case is not nearly as simple as this. So this is a nice case, but it may be misleading. Okay.
Sorry, Mike,
Yeah.
what, so you assert that this isn't a unique orbit, but presumably, I mean, you could have made some choice where you would have gotten line in the bottom half rather than the top half. So
oh yes. So first of all, you're picking a particular flag domain. So I've picked my flag domain to be like the upper half rather than the lower half. Okay, yeah. So I've done that. Okay, that's first off. And secondly, the base cycle is unique because I have chosen a particular maximal compact subgroup inside G0. If I pick a different one, I get a different base cycle.
Got it.
Okay, so I've picked D and I've picked a base cycle to start with. And that goes through in general, but what all the other cycles look like, that's in this particular case, it's kind of simple, but more generally, it's not. All right. So anyway, this picture, the picture that I've described so far, and more generally, gives rise to so-called double fibrations. And the title of this talk was The Range of the Double Fibration Transform. So now I just have to tell you about how you view all this in a little bit of a more exciting manner in order to get a transform associated with this picture. Okay, so story so far, G mod Q, which I've called Z. It has this domain inside it, which I've called D. D is a homogeneous space for the action of a real Lie group G0. Right, MD was this cycle space, space of cycles. Right? And no matter what, I mean, this is wherever MD is, I haven't told you, what MD looks like at all. Whatever it is, it's every point in that gives rise to a cycle inside D. And so you can encode that into a picture where what you do is you look at the subset of D cross MD, where you have a point in D and a cycle C from your space of cycles, so the point lies on the cycle. Okay, so the so-called incidence variety. Okay, and this is a completely general thing you might do. And this is called a correspondence. Okay, so some sort of terminology from algebraic geometry. Okay, so all I'm saying here is that this is just a fancy way of viewing the fact that MD is the space of cycles inside D, and a particular cycle corresponding to a point M in little m in MD is given by just taking the fiber of nu and pushing it down by mu. So, okay, so in our particular example here, we had P plus, we had M plus plus, which is the space of cycles. So P plus is the part of complex projective 3 space. M plus plus is part of the Grassmanion. And then you've got this incidence relation between the Grassmanion and the CP3. So you've got some sort of complex correspondence here, which is on the bottom right-hand side of the picture. And you've got some sort of open sub-arrangement of this. Okay, and this, as I said, this is all from a particular instance of this, which is called well, this is called the twistor correspondence. Okay, right. So what can you do with this? Okay. Now, unfortunately, as I mentioned already, unfortunately, what I've drawn so far, it's actually terribly misleading. And I'm just going to whiz through, just to sort of keep the gods of mathematics happy. I'm going to whiz through the fact that there are actually different types of flag domains and cycle spaces. So this is all thoroughly covered in the book by Fells, Huckleberry, and Wolf. But it's a little bit complicated. Okay, so I mean, what I've set up on the previous slide is completely general. This is just this, remember, this is this, this is this cycle space, M sub Z, okay? And M sub Z is just what happens if you move things around in Z, which is the cycle space, rather than just moving them around in D. Okay, and this is a homogeneous space, but unfortunately it can be quite an awkward homogeneous space, but nevertheless it's a complex homogeneous space. There's a relationship between J, which is whatever you get here as your stabilizer subgroup, and K, which is the complexification of the maximal compact subgroup of G0. Now, sometimes they're equal, sometimes they're not. Okay, I'm just going to whiz through this very quickly. All right, so I'm just putting this slide here. If we put the slides online afterwards, you can you can read through this carefully and make sure that this is all correct. And there's a really big distinction between the various things that happen. Okay, you can either have various things aligning very naturally, like this. This would be the simplest possible case. Or there are two other cases, like one of these things was another flag domain, which I've mentioned, but you'll notice I've suppressed because this one's kind of difficult. If you look at SU22, but just acting on this funny domain inside the Grassmanion, where it corresponds to lines which are neither in the upper half or the lower half, but really go from one half to the other half. Or there's other awkward spaces, and I've mentioned one of them already, and that's when you have SL4R acting on this complement of RP3 inside CP3. So this is a flag domain at the end. I mean, this is one of the most awkward. You look at a flag domain like that, the maximal compact subgroup of SL4R is SO4, and its orbits are, well, one of its orbits is a complex quadric, and then you move the complex quadrics around. Okay, so this slide is just designed to show you that these things are actually it gets quite involved at this stage. All right. The simplest case is the one that I'm outlining in yellow here, And that one has a name. It's called the Hermitian holomorphic case. Okay, so various nice things happen in the Hermitian holomorphic case. And for the rest of this talk, I'll just concentrate on what happens in this case. And other cases you can approach, but it's just awkward. Okay, so the thing is that what happens here is that, remember, you started with a flag manifold. So that is complex semisimple Lie group G modulo a parabolic subgroup, which for strange reasons I was calling Q. Now, it so happens that in this particular case, the cycle space lies inside a flag manifold, also lies inside a flag manifold. This is very unusual. This is the particular case we were discussing for the twistor correspondence. So all sorts of nice things happen. So anyway, so both of these things are now flag domains. Okay, and so just going down to the bottom right-hand part of the screen, you then have a correspondence in general, which is on the left-hand side at the bottom of the screen, versus what's happening on the right-hand side, which is all of these things are nice, really nice, homogeneous spaces for G. They are nice in the sense that what you're modeling out by is a parabolic subgroup, both on the left-hand side, which is where you started, and on the right-hand side. So all of these things are flag manifolds. Makes things a lot easier. All of these things are flag manifolds, right? So underlined, surrounded in a blue box here. This is important, but it's the simplest case. Now, in general, you may proceed. First of all, you ask about, what does this M sub D look like in general? Always, and this is quite hard theorem. A lot of activity on that in the mid 80s. Let's see, what was that about? In the 2000s and so. There's a full proof in the book. So there's a lot of ... here because lots of people are involved. But anyway, it turns out that this thing is actually a very nice, the cycle space is very nice. It's Stein and it's contractible. And the fibers of mu are also contractible. This is what allows you to make the following transform tick. So we don't have a transform yet, but soon we will. Okay, now the point is that D, this flag domain, is being not foliated, but it has lots of cycles inside it. This is the base cycle, C0, and then there's all of the other cycles. And they all have the same dimension, and it's traditional to note this dimension by S. And S is the highest cohomology, where the degree or highest non-vanishing option for where the cohomology might lie. So this is the sort of thing which is going to replace the top dimensional cohomology for the Barel theorem. So what we're going to look at in a moment is the S cohomology of D, and you're going to probe it by means of these cycles. Okay, so here's what you do. You have a homogeneous vector bundle on this flag manifold. So again, you can write them all down, very easy classification. Lots of things you can mark in your Dinking diagram at this stage. And then this is the sort of thing you might do. Okay, so if you have a homogeneous vector bundle and you pick a point in your cycle space, that gives you a cycle. So picking a point, that was called M. Your cycle is called C sub M. So that is a compact complex manifold. It's actually just a low dimensional flag manifold. In the particular example we were looking at, it's a line. Okay, so S would be 1. Anyway, so you look at this vector bundle, homogeneous vector bundle, you restrict your homogeneous vector bundle to that cycle. You get yourself a homogeneous vector bundle on the cycle. You look at its top dimensional cohomology, and you will get this, the result then as M varies will be a homogeneous vector bundle, HVB, on this cycle space on M sub Z, in particular on the cycle space M sub D. Okay, so let's call this vector bundle E prime. Right, so here's a fancy way of saying it. You pull back your vector bundle according to by mu according to this double fibration, and then you look at its S direct image under nu. Okay, and you do that, and then you get this. At long last, we are able to say what in general is this double fibration transform. What you do now is pick an element from your S cohomology. That's the top cohomology of D, with coefficients in this homogeneous vector bundle E. You go through this process of just restricting it to the various cycles, and you interpret the result as a section of a corresponding homogeneous vector bundle on M sub D, and that gives you some sort of transform. Okay, so the left-hand side is cohomology, the right-hand side is just sections. Remember that M sub D is Stein, so that's got a lot of sections. So it's an infinite dimensional vector space on the right-hand side, and generally speaking, the thing on the left-hand side will also be infinite dimensional. So this is now a transform between infinite dimensional vector spaces. Okay, and there it is. So written out in more detail, you take something in your cohomology, call it omega, and just restrict it to all the cycles. Okay? It's like doing various other integral geometric transforms, like the X-ray transform or the radon transform. So for the radon transform, you'd take a function of 2 variables and integrate it over the straight lines, or for the X-ray transform, you take a function of 3 variables and integrate it over the straight lines in R3. And this is like integrating something over a space of somethings. Okay, in this particular case, the integration is replaced by just cohomology and so on. Here's an example. Back to our standard example. We're looking at SU22 acting on CP3. Very, very simplest example is where P plus is the upper half of complex projective 3 space, and looking at this space. And for an example, you could take your original vector bundle, which is in general a homogeneous vector bundle. You could take it to the space of 3 forms. Okay, so let's do that. Okay, so in other words, this is in the classification of things as homogeneous bundles on CP3. You can think of that as just being well, it's a line bundle by dint of dimension, by dint of rank, and it's this one. Okay, so that's what it is in Dinking diagram notation. The pullback, you can develop a machinery, and there's a machinery for doing all this in terms of little Dinking diagrams and so on. I look at the direct image, then you get something down on the this Grassmanion or complexified, compactified Minkowski space, and it turns out you can identify that one as well. It's just a nice homogeneous vector bundle there. It's the it's half of the 2 forms. It's the self-dual 2 forms actually, and then there's some cohomological machinery which I'm entirely suppressing, which tells you what the range of this transform is. So, the title of this talk was the range of the double fibration transform. I've roughly indicated what the double fibration transform actually is, and here is what its range is in this particular case. So, first of all, P is injective. So that would be a general fine feature that you would like. You would like to interpret this cohomology on the left-hand side in terms of some natural submodule of the right-hand side. So P is injective, and here's its range. Its range is just the self-dual two forms which happen to be closed. This is really good because this is the Maxwell's equations in a vacuum. So these things have a familiar interpretation in mathematical physics. Here's the picture of the various forms that you have on Minkowski space. So 0 forms, 1 forms, 2 forms divided into self-dual and anti-self-dual forms, and so on. And what you get actually when you do this transform is that you get a part of this diagram. What you get is that yellow part of this diagram. And what you're looking at is the kernel of the very first arrow in this yellow part of this diagram. Okay, so all this is, I mean, the message here is that all of this is very, very satisfactory in this particular case. Injectivity is a key. One thing which is in the book, in the Fels, Huckleberry and Wolff book, is that this always happens, this injectivity always happens in complete generality if E is, well, sufficiently negative. Okay, so it means that when you look at E as a homogeneous vector bundle on the cycles, you have to ensure that not only is the cohomology concentrated in top degree, but it's better than that. Now, how much better is a bit of an issue. So Joe and I have shown that in the Hermitian holomorphic case, which is this earlier case, you can figure out what it means for E to be sufficiently negative. Okay, it means something in terms of just some little algorithm that you can perform by means of playing with Dinking diagrams and so on. The point is there's an effective algorithm for deciding this. This is what you would like in terms of your Dinking diagram. You want that these nodes are all non-negative, and there's an effective algorithm for doing this. Right? So that all works out very finely in the Hermitian holomorphic case. We've got some other cases worked out, but they're considerably more awkward. And what about the range? In the Hermitian holomorphic case, as I say, there's some machinery. This would be a typical Gmod P, which happens to be a compact Hermitian symmetric space in this particular case. You can figure out what all the, what everything is happening on the fibers by cutting these Dinking diagrams in an appropriate way. It's pairs of scissors doing that for us. You get some pattern which is down on Gmod P. These patterns are all very well understood. This is a sort of replacement for the de Rham complex, and it's a construction from representation theory, originally just algebraic due to Bernstein, Gelfand, and Gelfand's. So the BGG complex. And the sort of thing you pick up is that you pick up for the range. You get the kernel of just part of this BGG complex. So this is sort of typical. These things are all called Hasse diagrams. There's there's an algorithm for getting all this stuff out. It's once you've got the machinery in place, it's completely straightforward. Okay, that's all I'd like to say for the moment. I just say, that this article is very much a work in progress. Work in progress. I know this is a very concentrated talk. It's a bit difficult to give a talk about it because it's actually quite a complicated subject. Anyway, I would just like to say farewell, Joe Wolff. Thanks for listening, and thanks especially for Lois for coming along to this talk, and listening to me raving about mathematics. I know it was a bit of a rave rather than a comprehensive and congenial talk. But anyway, that's all I would like to say about mathematics. And I'd just like to end with a picture of Joe and Lois. I'm sure Lois will remember that they came to the ANU about 10 years ago or so, and this is taken at the beach on the New South Wales coast at Bateman's Bay, which is not so far from Canberra. Okay, that is all I would like to say. Thank you for listening again.
Thank you, Mike, for a really interesting talk about your work with Joe. Are there questions on the talk or questions related to the talk?
Hi, Claude.
Hi, Mike. So the example that you emphasized was the one of the Penrose transform for the future tube. Yes. And so there, the space is certainly a Hermitian symmetric space. But I gathered in terms of the way you phrase things that these domains are not always Hermitian symmetric spaces.
No. I mean,
that would be just the easy case.
Yeah. Exactly. That is the easy case. Yes, I mean, there are all sorts of special things. As Claude is saying, this is really very special, and you can see. You can see various other very nice features of this particular case. So, for example, in general, these things are Stein. Msubd is Stein, but in this particular case, you can look at in a particular affine part inside complex projectors inside the Grassmanion, and you can see that actually this thing is just a tube over a cone, and that's why it is Stein. And in fact, more than that, you can see that it is a tube over the future cone inside of ordinary compact, well, just the ordinary Minkowski space. So this is all really happening over Minkowski space, and not only that, but it's really, I mean, some other very convenient features happen that Claude knows all too well, and that is that see, one of the things you might think about is, well, maybe just the Maxwell equations rather than the self-dual Maxwell equations. That's a perfectly good space on which the conformal group is acting, but it's not irreducible, and even if you look at the self-dual ones, it's not irreducible. It splits into those which are so-called positive frequency and those which are negative frequency. And the advantage of the Penrose transform is that it makes all these distinctions, and it makes them all geometrically. So the fact that you get a tube over the positive cone is to do with these things being positive frequency. And then there's another space that you don't see. But in trying to endow these things with other structures, which physicists like making them into Hilbert space, and it's very important to make these distinctions, which are all sort of automatically encoded into the twist theory.
But am I right in thinking that already the general Penrose transform that you worked out in your book with Rob Baston,
yes,
goes a long way towards telling you what equations are solved, but it's not so clear whether.
So the book with Rob Baston is only for the Hermitian holomorphic case. So that's
what I was talking about, the Hermitian holomorphic case.
Yes, the Hermitian holomorphic case. Yeah, no, I mean the Hermitian holomorphic case is all, understood. Let's say that's all completely worked out, and it's basically in the book with Rob Baston. Yeah, that's correct. Yeah, that was another book I was going to hold up in front of the camera. There we go. So that's actually a reprint. It's a Dover reprint of a 1989 book. Yeah, I should say about the history. I mean, these various things were developed by various different people. You know, say in the 70s, you know, which, you know, different groups of people who were not, you know, talking to each other at all. And it's only more recently that these things have come together. Like, you know, the very first, you know, example, this is just ridiculous. The very first example of the Penrose transform, say for harmonic functions in 4 variables. Okay, so you can ask about, you know, what do harmonic functions in 4 variables look like? Do they have anything to do with holomorphic functions? Because of course, in 2 dimensions, they do. You know, harmonic functions are the real parts of holomorphic functions. What about a corresponding statement for harmonic functions in higher variables? And rather amazingly, in 1904, right? This is just bonkers, right? In 1904, Harry Bateman wrote down a formula involving holomorphic functions of 3 variables, which at least formally, you know, if you just differentiate under the integral sign and so on, give you harmonic functions of 4 variables, 4 real variables. Now it took from 1904, which is when this formula was written down, to approximately, let's say, 1976, when Roger Penrose was working on, you know, these various zero rest mass field equations and so on, to work out that actually the correct interpretation of Bateman's formula is by means of a Penrose transform, in the classical Penrose transform, which I've just been talking about, except it's done for, except you really have to do it for this non-compact real form of SL4 acting transitively on CP3. So strangely, you know, there's this sort of Euclidean version of twistor theory which captures this formula due to Bateman. But you know, if you want to trace the history back, you should trace it right back to Bateman in 1904. You know, which is just so lots of things you can find, you know, scattered in the dim and distant past, which all come together and can be grouped into one sort of semi-coherent bundle.
Are there any other questions? If not, thank you, Mike, for a wonderful talk.
You.